capability of simple low-cost VHF manual tracking systems to provide an ability to determine location in low precision without a transponder, multiple receiver installations, GPS, cellular service, or other satellites. I worked on this idea for some time with BLM and USDA ARS persons over the years. The WEST program gave me a great opportunity to try to bring it to life. Sold, for wildlife, are still VHF transmit-only types without location capability because of cost, size, and power restrictions. Cost is a huge issue as wildlife research is not well funded. The basic idea is that a modulated signal consists of many spectral lines or tones. The relative phase between these tones changes predictably with distance. If you have the right kind of transmitter and receiver, distance can be estimated without a transponder. By using multiple tone pairs, range ambiguities can be worked out. This is based on the tulurometer method used for microwave distance measurement. It is sensitive to multipath. However, for wildlands at ranges in the kilometers, the channel model work done so far suggests that at VHF frequencies, the multipath-induced error is better than typical manual triangulation error polygon, and it can be done automatically for similar costs. Demodulating the tones seemed pretty easy at first, but numerous challenges were encountered that make it very hard. However, before we could do that, we do need a transmitter and a receiver. The transmitter testbed is constructed similar to a VHF beep collar, with features making changes easy. It was built from junk box parts from the array of parts bins in my lab, and a microcontroller from David. Thanks, David. The transmitter uses a teensy microcontroller to BPSK modulate a 433 MHz keyless remote SAW surface acoustic wave oscillator. Now we have the transmitter, we need a receiver that can decode the modulation and tell which transmitter is present, as well as measure phase. So we need a modem, which turns out is a perfect thing for a WEST project since modems are a focus of the program. Specifically, we wish to implement an SDR, software-defined radio, digital modem, which instead of analog circuits like the transmitter, it uses samples of the signals as numbers and uses signal processing in an FPGA and a microprocessor. Such a modem has many, many parts. The major ones are and how they work will be very briefly explored in this video. Needless to say, each part is built by writing code, a lot of code, at least for an old analog person. The first thing we need to do is adjust the gain, kind of like the volume on your FM radio. It cannot be too loud or too soft. For the algorithms to work, it has to be Goldilocks perfect. This is called AGC, Automatic Gain Control. We also want to avoid division, because no one likes division, not even computers. For that, we use a feedback loop. Once the gain is right, we have to know when the transmitter signal is present so that it can be decoded. This is the job of the pulse detector. It uses a clever cross-autocorrelation ratio detector from the signal processing wizard, Professor Fred Harris. Thanks, Fred! This has the CIC Cascade Integrator Comb moving average filter to smooth out the noise also. Here it is doing its thing. That is, finding the part of the pulse we want. The transmitter also has an unmodulated portion that will be used for backwards compatibility and direction finding, if I ever get that far. The AGC actually happens at the same time as finding the pulse. Without noise, it is easy to see how the signal magnitude is adjusted to 1. Now that we know when the pulse is, we send its samples along. The next thing to do is make sure the frequency is tuned just right. For that, a special sequence is used with a single frequency Hilbert transform in the receiver modem. This allows us to determine frequency offset from angle rate of change of a complex baseband signal. Complex baseband samples are values like X and Y coordinates for modulation domain signals. The thing that adjusts frequency is another feedback loop. It measures the moving average of the angle and uses a second-order loop and a numerically controlled oscillator, NCO, to retune the pulse samples exactly to 0. The FLL is not actually perfect. It's pretty good, though. To get it perfect, we adjust the rest of the phase with a phase lock loop, yet another feedback loop. Here we use the costless loop so the modulation signal, which is BPSK, doesn't mess it up. After some more code, here they are both in action. This is actual over-the-air data being adjusted to the correct phase. We'll have to recover the clock timing. In order to know when to start doing that, we have to find the right spot in the signal, which is the preamble. This is accomplished with a cross correlator. Here's that doing its thing. again with recorded over-the-air data from the transmitter. The timing recovery algorithm uses a polyphase interpolation filter and its derivative version, along with a state machine to track all the marbles. This block took most of the time in the project. It was very hard to understand how to get to work with the many impairments that the transmitter had: rectangular pulse, noise, clock error and drift, as well as a severe frequency chirp. After a bunch more coding, here it is recovering data. This is also with recorded over-the-air data from GNU Radio. Here is a quick snap of the data that flows through all the blocks. Check out the report for endless detail on all these blocks. Now the modem more or less just spits out a little text at the end when it is working. Somewhat underwhelming for a YouTube audience. But wow, so cool for engineers! Now all this code has to be squeezed into the FPGA hardware. It was actually too much to finish in time, so the focus was the pulse detector. Once that is working, everything else follows the exact same process. All the code has to be rewritten in C, debugged, tested, then rewritten again for HLS high-level synthesis, and again for fixed point and used with logic libraries like shift registers. And add some more things to get it to work with existing drivers in Linux and GNU Radio for Zilibus. After all the code is tested, we synthesize it, move it to Vivado to build the project, and generate the bit file. The bit file tells the FPGA how to organize itself and talk to the processor running Linux on the Z-board. Z-board is using GNU Radio with a USB RTL SDR. The GNU Radio companion running on the Z-board takes in samples from the RTL SDR from the antenna and stuffs them into the FPGA as complex baseband. Pulse detector is on the FPGA and reports back to GNU Radio companion that it found a pulse. Once the rest of the modem is done, it will report the text ID of the transmitter and will be the starting point to come back to the distance estimation method. Here's a pulse detector doing its thing on GNU Radio companion. The pulse detector is implemented in the FPGA logic interfaced to GNU Radio with the Zilibus. The FFT shows a blip from the legacy pulse most of the time, occasionally catches the BPSK portion. The pulse counter increments each time the transmitter sends a pulse. This demo live over-the-air signals from the transmitter. Now seeing each of the major parts of the receiver modem demonstrated using recorded over-the-air data with the MATLAB model, and the pulse detector functioning in actual FPGA hardware, counting pulses from the transmitter. There is still a huge amount of work to do to get to a fully functioning system, and it's all very exciting. The entire process from algorithm development to hardware was successfully demonstrated, though, giving me a powerful toolbox to do great things in the future.